Van der Waals equations, and non-ideal gas behavior. And pressures. The behavior of real gases is consistent with the ideal gas equation, PV equals nRT. However, at low temperatures and high pressures, real gases stray from the ideal gas behavior. Therefore, the ideal gas equation is not applicable. In 1873, Dutch physicist Johannes van der Waals developed an equation which was relevant to the behavior of real gases over a large range of pressures. The van der Waals equation is a method of calculation used to understand the behaviors of real gases by introducing two parameters, constant A and constant B. There were assumptions from the kinetic molecular theory which van der Waals thought were ambiguous. One being that the gas particles occupy a non-significant fraction of the total volume of gas, and the second being that the force of attraction between gas molecules is zero. The first assumption, gas particles occupy a non-significant fraction of the total volume of gas, is true at pressures close to 1 atm. We understand that the relationship between pressure and volume is as the pressure increases, the volume decreases. Real gas particles occupy a finite and measurable volume. When the pressure is high, the volume occupied by gas particles is significant, no longer negligible, compared to the volume of the container. Therefore, the volume of gas particles needs to be considered. At high pressures, the volume of a real gas is greater than the calculated volume from the ideal gas equation. The equation which takes into consideration the volume of gas particles is P times V minus NB equals nRT. In this equation, the available volume is represented by V minus NB. B is the constant that is specific to a gas and is defined as B times 4 Na times 4 over 3 pi times r to the third power. Na is Avogadro's number and r is the radius of the molecule. The second assumption is true for gases at low pressures because gas molecules do not particularly have attractions between each other as they are at a far distance from one another. The intermolecular forces between gas particles deviate from ideal behavior at high pressures and low temperatures. When the temperature is low, the kinetic energy that gas particles have is less, making them move at slower speeds. This results in gas particles having a higher chance to interact as they collide. The ideal gas law does not take into consideration these interactions. When the pressure is high, gas molecules are in close range with each other, causing intermolecular interactions. To take into consideration the intermolecular forces between the gas molecules, the constant A is introduced into the equation. By adding this constant, van der Waals adjusted the slight reduction in pressures caused by the gas particles' interactions. In the van der Waals equations, the constant A and B are characteristic properties of a gas. Constant A corrects for the intermolecular attraction between the gas particles. The higher the value of A, the higher the intermolecular forces between gas particles, and the more it decreases the pressure of the gas and slowing down the speed at which the molecules move at. Constant B corrects for the excluded volume of gas particles. V is the volume, N is the number of moles, R is the universal gas constant, and T is the absolute temperature. At low pressures and high temperatures, constant A and B are negligible. Therefore, the ideal gas equation is applicable. At high pressures and low temperatures, the van der Waals equation is accurate and used to calculate non-ideal gas behaviors under these conditions. Moving on to sample problems that deal with the van der Waals equations. For every sample problem, there will be a comparison using the ideal gas equations calculation and the van der Waals equations calculations. Sample problem number 1. There is 1 mole of CO2 at 0 Celsius in containers of different volumes. A. Calculate the pressure of CO2 in a 22.4 liter container. The given values are N equals to 1 mole, R, which is the universal gas constant, T, which is given in 0 Celsius, and you convert that to Kelvin, which would equal to 273 Kelvin, and the volume, 22.4. You would plug all of these values into the ideal gas equation, and you would end up with a pressure of 1 atm. Now using the van der Waals equation to calculate the same question. The given values are N equals to 1 mole, R, which is the universal gas constant, T, which is equal to 273 Kelvin, V, which is equal to 22.4, and using the table provided, we would use the constant A and B for the compound CO2. Plug in all of the values into the van der Waals equation, and we would get a pressure of 0.995 atm. And as you can see when we compare the two values, at normal temperatures and pressures, the two equations will provide similar results. Calculate the pressure of CO2 in a 0.200 liter container. So using the ideal gas law first, the given values are N equals 1, R, which is the universal gas constant, and T is equal to 273 Kelvin, and the volume 0.2. We would plug it all into the ideal gas equation, and we would end up with a value of 112 atm. Now using the van der Waals equation, N is equal to 1 mole, R is equal to the universal gas constant, T is equal to 273 Kelvin, B is equal to 0.2, A is equal to 3.592, and B is equal to 0.04267. And we would plug these values into the van der Waals equation, and we would get a pressure of 52.6 atm. When we compare the values calculated by the ideal gas equation and by the van der Waals equation, we see that as the volume decreases and the pressure increases, the force of attraction between the CO2 molecules is strong, which results in a smaller value of pressure calculated by the van der Waals equation compared to the ideal gas equation. C. Calculate the pressure of CO2 in a 0.05 liter container. The given values are N is equal to 1 mole, R is equal to the universal gas constant, T is equal to 273 Kelvin, and V is equal to 0.05. Plug in these values into the ideal gas equation, and it will result in a pressure of 448 atm. Now using the van der Waals equation, the given values are the same as previously mentioned, with the addition of A and B. When we plug these given values into the van der Waals equation, we will get a pressure of 1,620 atm. Let's compare the two pressures. When the volume is very small, the pressure is very high, which results in the volume occupied by CO2 molecules being large. Therefore, the pressure value calculated by the van der Waals equation is greater than the value calculated by the ideal gas law.